Got it? What's that? Wait 2 minutes? But then I'd have to keep you all after class for an hour. Oh, okay. You can leave, it's all right. Say reverse Michael Jackson back there. I don't know what's going on there. He's wearing these black gloves. It's disturbing. Anyway, I will begin with a word of prayer before I say anything more incriminating. Anyway, dear Lord Jesus, I thank you for this day. I thank you for these students. Just pray that you'd help us to glorify you in what we do this day and just give us understanding, Lord. In your name I pray. Amen. So this is lecture 20. If I haven't been misled, I don't think I have. Lecture 20, which is going to be on group actions. And so your text has at its center in this section the goal of convincing you that group actions are the natural generalization that you need to make to understand how Cayley's theorem generalizes. And that's great, that's fine. But I'm going to take a different approach, which is just to state the definition of group action, show you examples, and then we'll probably along the way go, wait a second, we did this before. All right, so my approach is a little bit different. So my approach is what you might call unmotivated. So here's the definition. Let G be a group and S a set, then, and I'm going to assume that S is non-empty just for the sake of not being annoying, a multiplication of G on S is defined by, so what is it? I'm going to use a star for a little bit in here. It's a mapping from the Cartesian product of G and S to S again. All right. So I would say it's a binary operation, but that wouldn't be truthful because S doesn't have to be a group. S can be all kinds of weird stuff, as I'll expose you to today. It doesn't have to have any kind of group structure at all. All right. And yet there's some way that this G acts on S. This is called a group action. Star is the group action. It's a way of multiplying things in S by things in G. And this is called a group action. What is that? What is it required? If for each X and S, number one, well, sorry, and so I'm following my notes, by the way, guys. This is my AKA 2016 lecture 18 and 19. So point number one, 1 times X is equal to X again, and 2, all right, A acting on B acting on X is the same as AB acting on X. Oh, I see my stars have already degenerated to asterisks. Let me just commit to that from the start. It seems more likely that I can preserve that in some sort of stupid sense. So this, I mean, if you just think about this, this kind of makes sense, right? I mean, if there's a group acting on a set, surely the identity in the group should do nothing to the set, right? That's a kind of a natural idea. And also, if the idea of the group acting on the set is going to make sense, it also seems natural that we should have this sort of associativity of sorts, right? Now, there are many examples. Example 1, if we let G be a subgroup of the permutations which act on some set S. All right, permutations of S. Look at G as subgroup of some permutation group. Then you can define sigma acting on X by what? Well, remember that X is not, X is an element. So here, X is an element of S, but X is not a group element. X is not a permutation. I mean, it's not a, I don't know what sigma times X would mean. I mean, I can do something, but sigma's a permutation, right? So sigma's a what? It's a bijection from S to S again, right? Right, sigma of X. So, which is probably what Alan meant, and I'm just being a jerk, but anyway. Yes, and then the question is, does that define, does that define a group action? So what is required to check if this actually is a group action? Let's see here. First of all, how about the identity permutation acting on X? What's that equal to? That's going to be the identity permutation acting. But what's the identity? I mean, that's just, that fixes all elements. It fixes all X, right? So the identity permutations, of course, is in G, because G is a subgroup of the permutation group. And then what else do we have? If we have sigma acting on tau of X, right? Well, by definition, that is what? That is sigma of tau acting on X, which is what? Yeah, sigma, we can't write the sigma of tau of X, which is, by the way, sigma tau of X, which is, by the way, sigma tau acting on X. So there you go. That's the kind of associativity. That's item 2 we need. So if we have some object S, right, and we look at a subgroup of the permutations of that object, then there's a natural group action in this way. Can you guys think of another example of a group action we looked at before? Well, you were talking about left multiplications, right? Let's think back on that for a second. What was that for? Do you remember what we did? We said, so we can take G, we associate it with what? Left multiplication by G, right? What was left multiplication by G an element of? I mean, this is a mapping from G to G, right? And in effect, it's a bijection. I mean, that map is not a homomorphism, though, unless the group is special. I don't think, wait a minute, you're right. There's something in here that goes haywire. I'm forgetting what it is. Okay, anyway, I'm getting off track. So my point here is that LG is an element of the permutations on G, right? And I think we have that the set of left multiplications, like, is the set of left multiplications a particular subgroup of permutations on G? In other words, if I say H is equal to, say, L sub G, such that G is in G, does that form a subgroup? Is this a subgroup of the permutation group on G? Let's see. It's got the identity in it, right? Because left multiplication by the identity element's identity. If I have, LG times LG1 times LG2, and that X on X, that's G1, G2, multiplying by X, right? Which is, of course, LG1, G2 acting on X. That holds for all X. So you see that the composition of any two left multiplications is, again, a left multiplication. And also it's invertible. I mean, it's closed under inverses too, right? Because it's not hard to prove that LG inverse is LG inverse. Stupid English letting us down. Anyway, so the point is the group of left multiplications is a subgroup of the permutations on a group, right? And so this, we can of course then, I mean, there's a natural action of H, if you will. There's an action of H on G, right? So we can say H acts on the group by what? We say, so H acting on G is just given by what? Well, following example 1, it's LH, right? It's LH of G, but of course we know that that's just GH, right? Right, H. Oh, I'm sorry. I seem to have. Yeah, sorry about that. You're right. I should say LH, right? So sorry. Thank you, King. I can't keep track of my own idea. So anyway, my point is we already looked at the group action to prove, what was this theorem? That any group can be realized as a what? Subgroup of the permutation group. What was that called? Cayley's theorem, right. So, oh, wait a minute, that's a different Cayley's theorem, though, isn't it? It's different than the one we did last time, isn't it? What did we do last time? Cayley's theorem or did we do Cauchy's theorem? Cauchy's theorem, okay. My bad. Let's move on. So another example you could look at would be scalar multiplication of vectors, all right? But it's helpful for me, before I look at any other examples, to, I mean, there's a theorem that I should state. If G is group and S a set, then any group homomorphism from G into the permutations of S, all right, corresponds to an action of G on S, and conversely, every group action of G on S arises in this manner. I think for last year, this I gave a proof on October 14th of last year. I do not have it typed. Let's see here. I think we could at least sketch the core idea of this claim. Maybe we can just figure it out together. So what would a homomorphism, a group homomorphism from G into, suppose you have that, what would that be? Something like alpha from G into the permutations of S, right? Suppose that's a homomorphism. Now, supposedly that corresponds to an action of G on S. What do you think that action would be? Action of G on S. So I'm supposed to define G acting on X, right? Let G be in G, X in S. How are we going to build an action from the homomorphism? So let me just draw the arrow one way at the moment. So Sam says we should let it be alpha of G parentheses of X. That makes sense to me at least, because alpha of G is a permutation, right? So it's a mapping. So we can feed it a point, X. At least that's a well-defined thing. And where is that? That's an element of S again, right? Because alpha of G takes things from S to things in S again. So that makes sense. Is that going to satisfy our rules for a group action? Is 1 going to map to 1? So let's try it out. What happens? We do 1 acting on X. That's alpha of 1 of X. But hey, good news. Alpha of 1 is what? Is 1, right? Let's see here. Of course, that's the 1 in the permutations, right? On S. That's the identity map. So it should be denoted epsilon, except that I'm not insisting that S is a set of counting numbers. So, but yeah, if S was counting numbers, then I'd be all on board with using epsilon.
I just wondered because you used epsilon up there.
Uh-oh. You got me. You're right. I should really put the identity on S acting on X is equal to the identity on S, X equals to X. That would be better, since I think this epsilon symbol, I mean, it depends on notation. What notation do you want to use? Do you want to let the variable epsilon count for the identity in the permutations on any set? Or do you just want it to be the identity on permutations from numbers 1 through n? You go, what's that?
Any set sounds fine.
Any set sounds fine. So if you think that that's an abuse, then you should write what I just wrote in blue. Yeah. Anyway, getting back over to here, 1 is X, and then what about the associativity? How's that going to go? Associativity. If we have A times B times X, what's that going to be? A times alpha of B of X, which is what? Alpha, this is awful, alpha of A of alpha of B of X. But alpha of A and alpha of B are what? These are permutations, and alpha is a homomorphism. So this is alpha of AB acting on X, which of course is AB acting on X. Yeah. So anyway, that is a good part of the proof that Sam was right. That is how we should build an action from the homomorphism. How do we go the other way? How do you build a homomorphism from the action? Suppose you're given what's on the right-hand side. You're given the existence of star. How do you build alpha? How do we go from having a group action to having a homomorphism? How do I build alpha sub G, let's say, based on the, well, I shouldn't say alpha. Maybe I should say alpha sub star. It's the homomorphism built from the group action. How do I do that? I mean, I got to feed it a G, right? And then I need to define, that's going to be an element of the permutations on S, right? So to define that, what do I have to tell you? I have to tell you how alpha star G acts on something in S, right? And I think once you understand that, there's really only one thing you can write, right? Yeah, of course, there's more to do. I'm just giving you the core of the argument, not the entirety of it. But this is, of course, going to be G star X. And the fact that it's a homomorphism is just really nothing more than sorting back through the correspondence, and those axioms are the homomorphism property. And I think the 1 is what's necessary to get the bijection that you're talking about, King. Yeah. Okay, let me move on. Curses. I spent entirely too much time on that just now. My apologies. So you guys have a good weekend? Anything exciting? Did we lose? Did we win? No, we're having class, right? So, yeah. We lost again. Were there less than 15,000 in attendance, though? What's that? Because if there were less than 50,000 in attendance, we might be in trouble. The whole band was there? Just like every... Come on. So I'm about to give you the definition of orbit and stabilizer. Which are a lot like what they sound. Here we go. Here we go. Here we go. Maybe it's a, aha. There we go. Just use your error. Okay, here we go. So if we have a group action, there are a couple of very interesting things that we can calculate attached to this group action. All right? Here they are. So first of all, we can talk about the orbit of a point under the group action. This will be the set of all things that the group action moves that point to. Just what it sounds like, right? You start with a point, and you let the group act on it. Wherever the point goes to, that's your orbit. Very natural. There's also a stabilizer. The stabilizer of X, it's the set of all group elements which fix that point, all right? So a nice example of this would be rotations in the plane. It's pretty easy to prove that if you look at matrix multiplication on column vectors, this defines a group action, all right? So you can look at, but you can be more specific. You can look at the group of rotation matrices on the plane, right? So if you look at any point except for the origin, and if you look at the action of the set of rotations in the plane, what are you going to get? You're going to get actually an orbit, a circle, as you think about rotations moving that point around, right? On the other hand, if you look at any point other than the origin under rotations in the plane, right? The set of points, the set of group elements which fix that point, what are the rotations which fix the point? Reflections will take the point and move them back over here, though. It's just the identity. Unless the point is what? The origin, right? If it's the origin, then everything fixes it, right? So there's a big difference between points in the plane which are not the origin. Those have stabilizers which are just the identity, the stupid group. And then the origin, the stabilizer of rotations in the plane of the origin is well, it's everything. I have more explicit examples just coming up. You can also talk about the subset fixed by G. So that's the set of all points which are stabilized, right? So like the fixed subset of the plane under rotations is just what?
The origin.
Just the origin, right?
Well, but like if you reflect and then you rotate 180 degrees, would that still fix?
That's the identity again.
That is the identity?
Yeah. So one of the group actions you can look at is, let's see here, example 2.93. Let me go back to that just a second. I had a few more examples in my notes than I had a chance to write up here. So this is another group action you can define. If you have H a subgroup of G, you can let H act on G according to just group multiplication, right? So you can let a subgroup of a group act on the whole group by group multiplication. And it in fact defines a group action because the group properties give you 1 and 2. And so if you think about this group action, what's the orbit going to be of a point? What's that? The coset, right? Left or right? Yeah, you're right. You're right. I'm sorry. It was messing with me. I wanted to say left for a second, but you're right. I mean, you're correct. So you can also look at this oddball group action. If you multiply on the right by h inverse, that will also satisfy. I shouldn't even show you this. I should make this a homework. Oh well, it's too late. So you can also take the subgroup and make it act on. You can make it act according to this rule. That'll give you yet a different group. And this time, what would the orbit be of x? The left coset. It would be xh. That would be the orbit for that one. All right. So again, so this is the multiplication by elements. So just like Kang was telling me a second ago, the right coset. What's the stabilizer of x? It's just what? It's exactly h, right? So if you look at the group action given by scalar multiplication, you can argue that the orbit of v equals to 0 is just the origin, because if you scalar multiply 0, you just get back to 0 again, right? But if you're looking at v not equal to 0, right, then the stabilizer of that v is just 1, right? Because how do you get from v to v again? By scalar multiplication. Scalar multiply by 1, right? If you look at the orbit of v, it's what? Right, it's everything except for what? Like I said, CV gives the line with direction vector v with the origin removed, since the group we're looking at is non-zero scalars. So I don't know. I think I would encourage you to read these examples and try to get. It should give you a decent understanding of what a group action is. But this one we've already studied. So another group action that's interesting is this one, G acting on X by GX G inverse. This is an action of the group on itself. In other words, conjugation is a group action of G on G. And so here's the proof that it satisfies the two axioms. Great. But what's more interesting is what's the orbit under this group action of a point? We talked about this last time, right? We called this what? This was class X last lecture, right? So the class of X is the orbit under the conjugacy can't talk. Conjugacy group action. Stabilizer, centralizer of X is what? I'm saying the stabilizer is the centralizer, see, because if under conjugation you go back to X again, well, that's the same as saying GX is equal to XG, right? And we also called this what? The normalizer of X last class, right? And then what's the fixed subset with respect to this group action? That's exactly the center. So all three of these things, orbit, the stabilizer, and the fixed subset, these are all very interesting. To understand a group action in some sense is to carefully understand these three objects and how they work, right? Here's some simple things that should keep you straight. The orbit should be a subset of the set on which the group acts. All right? The stabilizer, G sub x, is a subgroup of the group which is acting. And the fixed subset is, again, a subset of the set on which the group is acting. If you remember those three kind of just where things are, that'll keep you straight a lot of times. So one of the things, of course, you want to prove, one of the first things you want to prove, and this is a great test question. Like this one, this is a just straight down the middle, friendly test question, If G is a group which acts on a set S, then prove that the stabilizer is a subgroup of G. So how do we prove that? So first of all, you got to know its definition, right? Curse the cursor. G sub x, G and G such that Gx is G again, right? So first of all, the identity of the group, I used E last year for the identity, sorry. Set E equal to 1. Not good for calculus, but it works for us here, right? So definitely the identity is in the stabilizer, right? And how about if you take two things in the stabilizer? Suppose A and B are in the stabilizer of X. Then AB acting on X is A acting on B. This is by axiom 2 of the group action, right? But remember, B acting on X is X again because B is in the stabilizer, right? But then A is in the stabilizer, so you get back X again, but this is exactly what it takes to be a member of the stabilizer. So AB is in the stabilizer of X. So by the subgroup test, and here's the proof that the inverse is also in there. So by the subgroup test theorem, we get that this is a subgroup of G. All right? Next theorem, which will feel a lot like what we did last class. If you have G as a group and it acts on a set, then the orbits partition S. All right? Moreover, for a finite set, the order of S is the sum over the sizes of the partitions. It's the sum over the sizes of the orbits, right? Now what's different here is last time we just talked about what? Our orbits were conjugacy classes, right? Here I'm not supposing that the orbits are conjugate. They could be a conjugacy class, but they could be other things, all right? And I have explicit examples to show you in a minute. Yeah, okay. So here's the proof. Basically, what you want to do is prove, how can we get something's a partition? The easiest way to do that, to prove that, is to prove that we're working with a what? An equivalence relation, right? So we want to show, what is our equivalence relation going to be? It's going to be 2 points in the set are equivalent if and only if what? They're in what? The what? So King is giving me the details of what it is. There's a G that multiplies one point to the other. But what that is tantamount to saying is that they're in the same orbit. Right? So 2 points are equivalent if they're in the same orbit. So that's my equivalence right here. X equivalent to Y if you can get X is equal to G star Y. So first of all, X is equivalent to X by axiom 1 of the group action. So it's reflexive. Symmetric, if we have X is equivalent to Y, that means that you have this, right? But if you have that, you can act on both sides by G inverse. So if G moves Y to X, then G inverse will move X to Y. And that's what I did. I multiply both sides up. This trick right here is pretty much what like tons of proofs are basically based on this one silly step. But anyway, there it is. So that's not reflexive, that's symmetric. And then if you have the X is related to Y and Y is related to Z, then you get G and H such that and that. And so if we look at, we have X is like so, which is by the associativity axiom that, and that's an abusive language, it's not actually associativity, right? Unless your group action actually happens to be multiplication inside a group, then it could actually be just straight associativity, but whatever. Anyway, so that shows you that X is in the orbit of Z, which means that that's transitivity. Okay, so anyway, long story short, this is a equivalence relation, which means that the orbits, which are what? The orbits are the partition afforded by that equivalence relation in the language of chapter 0 in Nicholson. So they partition the set, and then it's just counting, right? So, but there's more. If G is a group which acts on a set S, and X is an S, the elements of the orbit of X are in one-to-one correspondence with the left cosets of the stabilizer of X. So one-to-one correspondence between the orbit of X and the left cosets of the stabilizer of X. And the index of the stabilizer is the size of the orbit, which is to say that the size of the orbit is the index of the stabilizer, Gx and G. What was your question? I have examples of this theorem. I mean, we can prove this. Basically, the bijection is given here, F. It's kind of complicated the way it's defined. And we could go through this proof, and you know what, if we did, it would be enjoyable to some of us, but it wouldn't really leave you much better understanding of the orbit stabilizer. I mean, this is the orbit stabilizer theorem. I probably should prove it, but you notice me walking back towards this computer. Actually, the corollary is the orbit stabilizer theorem, which is that if a finite group G acts on a set, then the number of elements in any orbit must divide the order of the group. What? Check that out. If a finite group G acts on a set S, then the number of elements in any orbit must divide the order of the group. So that means if I have a group of order 20 and it acts on a set, what are the possible sizes of orbits? I guess that's it's a finite set? Set. No. I don't think S has to be finite, does it? No. But yeah, then so if we had group of order 20, then the orbits would have to be what? You told me either 1, 2, 4, 5, 10, or 20, right? So you can't have a group of order 20 act on a set and get an orbit with 7 things in it. Like, that just doesn't happen. But it's better than that. The order of the group is the product of the orbit of X and the stabilizer of X. The cardinalities of these, respectively. So the proof is essentially by the theorem that I didn't just prove. Sorry about that. I will probably feel guilty about this and come back and prove it Wednesday. But we'll see if I get that guilty. Anyway, for a finite group, right, the number of cosets is the what? That's the index, but it's also the order of the group divided by the order of the subgroup, right? So since this is what the last theorem said that was the orbit, the size of the orbit, right? Then if you just look at this equation, that gives you the stabilizer times the size of the orbit is the order of the group. Yeah. This allows for beautiful counting problems. Here's one. So if we think about a square, right? Actually, what we're thinking about is important to identify the set of objects which we're going to act on. All of my examples up till now in class have been kind of boring. They've been, like just an arbitrary set. I didn't even tell you what it was, right? Or I talked about the plane, right? Talked about a group. I mean, all of our examples have been kind of abstract. Here's something much more concrete. But the point of keeping those examples abstract, in part, was so that that set I was talking about earlier could be like this set, right? Anyway, so set of vertices of the square. So you can think about a group acting on those. So he says, listen to me, I said, there's a natural action of D4 acting on S, right? D4, dihedral group. And how does the dihedral group act on the vertices of the square? Just by like the natural geometry, right? So D4 either has rotations by 90, 180, 270, or all the way around, right? And then you've got the reflections, all right? There are 4 of them. The 4 reflections are like the horizontal, the vertical, and then across the 2 diagonals. These are actually the geometry of those. Here's a picture of each one of the elements of D4. The identity, this is rotation by what? So to get from here to here, we rotated 90 degrees, right? I guess clockwise. And then that's by 180, and that's by 270. These are actually clockwise rotations. I don't know why I did that. Oh well. I usually think counterclockwise, so these are a little bit awkward. My apologies. Anyway, and here's the reflections. I've even drawn in the line of reflection for each one. Right. Okay. So the group which is acting is D4. The set on which it's acting is the set of vertices, right? And you can look at orbits, right, of different. Pick any vertex in this square. What's its orbit under the group?
All of it.
Yeah, it's the whole thing. So any vertex will be rotated to the others, right? I mean, so any vertex can be rotated to the other, moved to the other by an appropriate D4 thing. Incidentally, here's the other theorem we were looking at in terms of like subgroup of the set of permutations on the set. Here are the literal permutations written in cycle notation that correspond to D4, you know. The identity rotation. Well, anyway, I'm getting stuck in the weeds here. So what's the orbit stabilizer theorem say? So the orbit of any point is everything else. What's the stabilizer of the zeroth vertex? Which group actions keep V naught stabilized? Identity and reflection. Let's see. Identity, I'll totally agree with. And what's this V1, V3? Which one is that up in the picture?
Lower left.
The lower left. So what are we? So this is the zeroth. So this upper vertex is fixed under that reflection, right? We agree. So the stabilizer of the zeroth vertex is the identity in that particular reflection. And so there you have it. The size of the orbits for the size of the stabilizers 2. What's the size of the group? 8. So 4 times 2, 8. Great. Here's something a little bit more interesting. 6 faces to a cube, right? So you could think about, so if this is, let's call this thing, I don't know, I need to come up with a name for it. How about C? For cube, right? And we can talk about the symmetries of the cube, right? What are the symmetries of the cube? It's been a while since I introduced this, and I didn't test you on it, but that should be the subset of permutations on the cube, or you could say it's. I mean, fine. I can look at C as a subset of R3, right? And I can look at this as being a subgroup of the permutations. Or what did I want? I didn't want permutations. I want the subgroup of the isometries, right? On R3 that do what? I mean, if sigma is an element of here, what's sigma? Sigma C is what? It's C again, right? And here I mean the capital C, not like a lowercase. I mean the whole cube. So it's the set of isometries which fix the cube under. So like, how can you take the cube to a cube under an isometry? Them's rotations and reflections, assuming the cube is where, like centered at the origin. You've got like rotations this way or that way or the other way, and you can reflect across like diagonals, and so forth. But anyway, if you think about the symmetries of a cube, you can understand those in a lot of different ways. You could look at the set of vertices of the cube and how a symmetry of the cube would send a set of vertices to a set of vertices, right? That seems like kind of a drag because how many of there are? What, 1, 2, 3, 4, 8 vertices, right? But faces, how many faces do you have to a cube? 6 faces, right? And if you think about a particular face, how can we fix this? Let's look at this face here, the front face. this face, how can you fix, what's a symmetry which leaves the face, what's this, sorry. So the set I'm thinking about is the set of faces, F1, F2, F3, F4, F5, F6, right? The set of 6 faces. So we can ask, what's the stabilizer of face 1, let's say? Right, what's the stabilizer of the subgroup of symmetries of the cube which stabilizes face 1? Yeah.
Kind of like in our other example, because you're kind of reducing this to just that rectangle rotated to stay the same.
Right, I think it's very much like the first example. So yeah,
Reflected, otherwise it'll switch the direction of the cube.
well, I don't think the cube has a direction, but
Move the cube.
oh, it'll move the cube. Yeah, yeah. So certainly we've got the rotations, right? So it's got 4 rotations, right? Because you can. Are there any reflections or anything else? What's that? By what? Ah, so you're like, if I kind of like flip it over this, is it this plane or no?
Look at the X, Y plane or the Y, Z.
It should be exactly the same as our last example. It's just the symmetries of the face.
Ah, very good. So there's 4 reflections. I just am having trouble. So you guys already saw it. I'm having trouble reading my own notes. Good. But yeah, that's the point actually, is that there are 4 reflections and 4 rotations. What? No, that's not what I said here. I don't believe you guys.
They're just the same. Reflected and still going to get the same as doing rotation.
The stabilizer of a face. I don't. Oh, but you know what? Those there's a reason I have to rule those out. What's that?
Isn't reflecting it over that plane just the same as 2 rotations? Yes.
Oh, okay. So then that's just double counting, is your guys' point. Very good.
Wait, isn't that because when you, like, if you label those, like starting at the top left, labeling 1, 2, 3, 4, kind of like the same as we did in the previous example. If you just reflected by that, you would still have, you'd have 1 and 2 on the bottom, 3 and 4 on the top, but it would flip the direction of them if you actually rotate it twice.
Right, but we're not thinking about we're not keeping track of which vertexes were which. We're looking at it as a face.
Are we restricting it to like rigid motions of the cube? Because like you can't like
Yes.
push the cube through itself kind of in that sense, even though that takes vertex.
Well, again, symmetries of the cube. So I think that has to be the isometries of R3 which fix the cube. Which, I mean, I know it means we can either rotate the cube or rotate, reflect it along an axis through the cube. Like, let's see here. So if you think about, of course there are the rotations about the axes of the faces, right? But another motion is if you look at like this diagonal axis, you can like rotate the cube like that and get back where it started. But we don't distinguish those. We're looking at the face of the cube, right? Any rotation will fix the face, but anything else is moving the face, is what it boils down to. If I look at rotations around the vertical axes, right, I'm going to shift the front face to a side face or a back face, right? That's not stabilizing. And if I rotate this way, then I'm shifting the face from the front to the top or to the back or to the bottom. And any of these weird, come on, what's going on here? Oh. This is much worse than a connection problem. This is my battery being dead. That's not a one we can come back from easily. Anyway, the point of that example was what? You have the stabilizer of the face has order 4, right? Admittedly, we need to think more carefully about what exactly it is we're counting. Agreed? But the stabilizer has order 4, and what's the orbit? Like, I mean, what is the orbit of the face under group symmetries of the cube? Well, you can move to any of the other faces, right? So it's a transitive action. Any point moves to the other points. The point is the orbit has size 6, the stabilizer has size 4, so the group of symmetries of the cube has 24 things in it. That's the kind of neat thing here. Is it's pretty hard to like actually enumerate those, but it's a simple matter using the orbit stabilizer theorem to count how many symmetries there are in the cube. That's the point of this example. Anyway, I will try to say more interesting things Wednesday. My apologies about that.